Okay, chapter 2 deals with the physical environment. And here we'll walk through some concepts around climate, climate variability, and how that impacts ecological systems. And so really, both from a future, current, and historic standpoint, understanding climate's fundamental to understanding the physical environment and understanding how ocean and wind currents impact these ecosystems. And large-scale atmospheric and oceanographic circulations establish these global patterns of temperature and precipitation, which then derive our ecological communities. And regionally, you can think about how come Western Washington looks different than Eastern Washington, and in context of the way that continental and oceanographic forces play out between Eastern and Western Washington. And these seasonal and decadal climate variations are associated with both. There's really interesting decadal oscillations that are happening, as well as just how the Earth naturally tilts and moves around the sun. And these influences, particularly in oceanographic systems, have profound impacts on the physical parameters important to those ecosystems: salinity, oxygen, acidity, things like that. We'll come back to this example later on, but it's a pretty interesting case study looking at climate variability and salmon variability around the Pacific Decadal Oscillation. And the PDO, as it's called, is really interesting and has some good grounding, but it might be breaking down in the future. And it's, to me, one of the most important things to know about as it relates to why we see variation in fisheries abundance. Maybe not the most important, but it's a one of the key factors. There's many other factors we'll talk about. And so salmon are very important, obviously, in the Northwest. This doesn't need to be that reinforced. And then traditionally, salmon has been thought of as the 4 H's: habitat, hydro, harvest, and hatcheries. So traditionally, there were 4 things we thought about when we cared about salmon: habitat, they need places to spawn and rear; hydro dams; harvest, how many we catch or kill; and then hatcheries, releasing additional salmon; and then wild salmon, wild hatchery interactions. And then for quite a while, that was the 4 H's of salmon, of the salmon world. And then we realized the ocean's important, but we didn't want to change from 4 H's, so now they added a 5th H of ocean, of ocean. So if you think about Pacific salmon, 5 things that you need to consider: habitat, hydroelectric power, harvest, hatcheries, and oceanographic conditions. And so we'll return to that last factor as it relates to the Pacific Decadal Oscillation in greater detail. And so this work was really kind of broken open by Hare and Francis, 1994. We'll go back and look at one of Hare's 99 papers in the second half of this lecture. But realizing that there's this really important interaction between the Aleutian low, a atmospheric condition, and ocean circulation, and how that relates to the primary productivity of these systems, subsequently zooplankton, and ultimately salmon returns. And so what this graph is showing are periods of relatively high and low return, which they then related to the Pacific Decadal Oscillation, or what later became known as the Pacific Decadal Oscillation. These are Alaskan returns, and there's an interesting story about the inverse relationship between positive productivity in Alaska and positive productivity down here in Washington, Oregon, southern BC. So they actually alternate When Alaska is doing well, Washington is doing poorly, and vice versa. So we'll break this down and really kind of talk about what the PDO means in the second half of the lecture. In the first half, we're going to focus more on the physical environment, which is ultimately drives where organisms live. As I mentioned, I think in the prior lecture, that it's really extremes that drive populations, not necessarily means, meaning the extreme rainfall or extreme drought, not average rainfall. But understanding the physical environment is key to I wouldn't say dissecting, that's just fair, deciphering the structure behind ecological communities. And of course, climate and weather are different. Weather is what we're having today. Climate is the long-term version of that weather. So it's important to look at overall trends, like one really warm day or one really cold day is a weather phenomenon, but a occurrence of repeated warm days over many years is a hint at climate variability. And so long-term climate change results from changes in intensity and distribution of solar radiation, and climate change is impacted by greenhouse gases. And so really, when we talk about climate change, I like to think about it from the first principle, right? First principle is solar energy is coming in. We'll learn that some of that's trapped, some of that's released. Adding more greenhouse gases increases the amount of the energy that's trapped. And so by definition, from first principle understanding, climate gets warmer on average and changes with increased absorption of that energy from the sun. It's really just that simple. It's just basic first principles of energy comes in, a certain percentage of energy leaves, and as we do things that trap more of that energy in the system, there's more energy in the system. It's really just that straightforward. It's not a big complex concept in my mind. It's extremely straightforward. And here's an example of extreme high temperature droughts from 2000 to 2003 that killed a lot of pinyon pine throughout southwestern U.S. And so images of the same area. You can see the background here, this like little hill and the second hill are here and here. So this image is taken in the same spot just a few years later, and you can see that many of the dead trees still standing here. And so these sorts of lines of evidence I think are really powerful. Repeated images in the same spot I think is really powerful. These visual of like kind of hit you in the face images I think explain what's happening quite well. And so if we again kind of go back to first principles, we can walk through this diagram of looking at, I'm kind of in the way here, just walking through what happens in percentile bases of energy that comes in, where we've got incoming solar radiation. Some is absorbed by the surface, some is absorbed by the atmosphere, some of it's reflected back out. Sensible heat and latent heat, which we'll learn about. And then this interaction between energy emitted by the Earth's surface, what's trapped in greenhouse gases, what's absorbed back by the surface, and then what's leaves through outgoing long wave radiation. And so as we add more greenhouse gases, we're keeping more energy in the system. So much of the Earth's solar radiation is absorbed by the Earth's surface, is emitted to the atmosphere as infrared radiation. The Earth's surface is cooled when water at the surface evaporates and absorbs that energy. And latent heat flux is heat loss due to evaporation. So as it takes energy to move liquid water into water vapor, and so that energy is absorbed in that state transformation. And that absorption of heat is called latent heat flux. And we have kind of three general terms we'll think about as it relates to heat transfer: conduction, convection, and sensible heat flux. Conduction is kinetic energy transferred by molecules in direct contact with one another. Think of it as heating the surface of the Earth, and then a centimeter down, that's also warming. Convection is energy transferred by movements of air and water. We'll talk about that around the conveyor belt, which is how heat's moved around the globe via the ocean. And then sensible heat flux is energy transfer from warm air immediately above the surface to the cooler atmosphere by convection and conduction. So movement of heat from the right above the surface of the Earth. Greenhouse gases. Water vapors, one. Carbon dioxide and methane are probably the two biggest ones we talk about as it relates to anthropogenic impacts. Although we are impacting the water system a lot via development and changing vegetation communities. And then nitrous oxide, we typically talk about around the car emissions and things like that. But generally, methane is about 20, the numbers vary, 25 to 50 times the greenhouse gas that carbon dioxide is, although we do spend a lot of time thinking about carbon dioxide. Now, I often say if there's only, if there's only one graph that in science, the Keeling curve is probably the most important. This is the Keeling curve. I'll jump to the next image, which is the carbon dioxide values for today, and then talk a bit about Charles Keeling and then now Ralph Keeling. So this graph shows carbon dioxide values at Mauna Loa Observatory. And this is carbon dioxide through time, starting in, I believe, 1958. And these data are from yesterday, where the value is 141 parts per million of carbon dioxide. What Charles David Keeling set out to do, he was a faculty member at Scripps Institution of Oceanography, where I did my doctorate. He was hired by Roger Revelle, a famous oceanographer and former director at Scripps, to measure carbon dioxide in the atmosphere. And he and Revelle had a pretty fierce argument about how to do that. Revelle wanted like a network of carbon dioxide measurements around, ideally the globe, but around the US. And Keeling felt strongly that we needed to find a spot that had the minimal amount of nearby anthropogenic contribution and make that like a sentinel site where we develop a long-term record. And so when we think about the same way we think about sample sizes, and we think about long-term data sets and effort, if I only have so much effort, is it better to put it all in one spot and have a really rigorous data set where if I see a change, I can say something and I can interpret local contributions to that? Or is it better to have a wide, given a similar amount of effort, money, staffing, equipment, etc., is it better to have fewer points of data from each location, but then have lots of locations? So instead of being able to invest in daily measurements from one spot, maybe I do weekly measurements in 7 spots, right? How do we maintain all those locations, and then how do we interpret those results when we have them weeks, years, months down the road? Keeling was a CO2 nut. There are stories of him going camping and bringing, they sample the atmospheric air using vacuum flasks. And so they're like these giant glass balls. They suck all of the air out and then they crack the valve and it sucks in atmospheric air. He would bring these with him wherever he went, and he was always sampling air. And he felt really strongly about finding a spot high in the atmosphere with relatively little nearby impacts and monitoring that over a long period of time to develop a global signature. And so Ravel really wanted multiple sites. Keeling ultimately came out, won the argument, and so they developed the Mauna Loa Observatory. Now, Charles David Keeling has passed, I think, more than a decade ago now. And his son, Ralph Keeling, now runs this program. So it's sort of interesting. His son wound up going into atmospheric sciences and studying carbon dioxide just like his father. Occupies the same lab his father did at Scripps. Uses a lot of the same equipment that's been around for a long time to maintain this record. And this record has a few things of note. One is there's an annual variation in carbon dioxide. And then there's an interannual, a long-term trend. And so one thing that's really important is you can imagine if each of these points of data had error bars of 10 or 20 ppm, parts per million, it'd be very hard to discern this trend. But their method's quite good. And so this alternation of high carbon dioxide, low carbon dioxide within the year is driven by the distribution of land. And so there's more land in North America than there is in not North America. There's more land in the northern hemisphere than there is in the southern hemisphere. So during our northern hemisphere summer, there's more photosynthesis going on, more carbon dioxide being absorbed. When the summer moves to the southern hemisphere, there's a smaller amount of land mass, so there's less primary productivity overall. That leads to a net increase in carbon dioxide in the atmosphere. So during our winter, there's more carbon dioxide in the atmosphere than there is during our summer, globally driven by this distribution of land mass and subsequently vegetative potential. So that explains the yearly wiggles. Now there's a long-term trend here of increasing carbon dioxide. And you can look at the amount of fossil fuels we've burned, and you can look at the isotopic composition of that carbon dioxide through time. And when you burn a fossil fuel, it's a very old carbon, right? If I grow a tree for 5 years in my backyard, cut it down and burn it, the carbon released is only 5 years old. Now, if I drive around in my car and I'm burning fossil fuels, that carbon is very, very old. And so it's actually exceeded the lifespan of C14 dating. And so we can C14 date atmospheric carbon and get an idea of what percentage of that's from really, really old carbon and what's from newer carbon. And so we can use that differential to figure out how much carbon dioxide's built up in the atmosphere from old carbon, from fossil fuel. And those calculations match what we're seeing now. And so there's multiple lines of evidence we have to seeing that the rise in carbon dioxide is due to anthropogenic impacts. Now, the attack is always, climate scientists are doing this for the money. They're just a fair number of bad words. And I got to know Ralph a bit, Charles' son. Mostly, he would go out and surf in the morning, and I'd see him in the lineup and stuff like that. Really kind of understated guy, and not really, he's just a geek who likes carbon dioxide. And I actually ran into him in the weekend once at Napa Auto Parts. He was buying parts for his mid-90s Subaru wagon. So here's a guy who drives an old beat-up car who is going to the auto parts store to buy parts to fix his car himself. To me, not the sort of individual who is motivated by financial interest. And so I always think about that when I hear, certain segments of the population talking about how we're all just in the pocket of green money or whatever the conspiracy theory is, that here's the guy who is now the steward of arguably one of our most important pieces of data, who goes down to Napa Auto Parts on the weekends to buy spark plugs for his mid-90s Subaru. That was a while ago. He might have a Tesla now. I don't know. But nonetheless, not the villain that some will believe the climate scientists are. So this is driven by the difference in solar radiation. And this is hopefully a review, but if you just think about light, if you think about holding a globe up and shining a flashlight at it, the light is brightest at the equator and then fades out as you go north and south. As that light, as there's a disproportionately more amount of area to absorb that same amount of energy. So this diagram shows it quite nicely. We've got light coming straight in. All of that light is absorbed by a relatively small area compared to the similar amount of light hitting the North Pole over a much broader area, and similarly in the south. And so that's the fundamental driver of living on a sphere. If we lived in a flat Earth, it would be a lot different. So it'd be harder to explain oceanographic and atmospheric currents on a flat Earth. But in fact, our Earth is round. So that's one of the major fundamental drivers of climate. Solar radiation heats the Earth's surface, which emits infrared radiation and warms the air above it. This pocket of warm air is less dense than the cool air, and it rises. Again, back to first principles, density, lighter things float on top of heavier things. And atmospheric pressure decreases with altitude, so rising air expands as the air and the air cools. And so you've got a pocket of warm air rising off the surface. It's warmer, so it's lighter, and as it moves up, it expands. And so you can think about, like, if you let a balloon go, which you shouldn't, but if you let a balloon go, it eventually pops because it just expands, because there's less atmospheric pressure, so there's less pressure pushing in on that balloon. Same idea with air not in a balloon. As it rises, it expands and then cools. Goes back to like the gas law principles of expanding and contracting air. So here's an example of that. Warm surface, warm air, cool air coming underneath, and that starts to rise. As that warm air rises, water vapor becomes clouds, and then that air then starts to lower back down. And so that's the one way we get cloud formation or water particulates in the air. And generally, we've got a couple large circulation patterns. The first are referred to as Hadley cells, and that's where we've got warm, water-rich air rising from the equator, creating cloud formation that then ultimately, through subsidence, comes back down to the Earth's surface and releases precipitation. And so this circle of movement of air and water between 0 and 30 north and south is known as, or driven by, the Hadley cells. Lots of things named after people coming up. So subsidence is air that descends when it cools and forms a high pressure zone about 30 north and 30 south. Major deserts of the world are in these latitudes, and the Hadley cells, large scale circulation patterns resulting from uplift in the tropics. We also have polar cells, Ferrel cells, that we'll look at in the next diagram, that explain a lot of additional circulation, and these circulation cells are or result in our major climatic zones, both tropical, temperate, and polar zones. And so we have our Hadley cells. Moving further north or south is a Ferrel cell and then a polar cell. So HFP, Hadley, Ferrel, and polar cells. Polar cells are easy to remember because they're at the poles. Hadley, I thought there was I thought there was a good mnemonic for that. And then Ferrel above that, these kind of wider cells. So these atmospheric circulation cells create surface wind patterns. The air flows from areas of high pressure to low pressure. We'll walk through that a bit when we get to PDO. results in consistent air patterns called prevailing winds. And the earth winds are deflected due to the Coriolis effect. And so in the northern hemisphere, things move to the right. And in the southern hemisphere, things move to the left. So here's an example of the predominant direction of our winds. Trade winds moving from the east to the west, westerlies moving from the west to the east, and easterlies again coming from east to west. And wind, you call the direction of the wind. And so if we say we're having a western wind today, that means the wind is coming out of the west. Southern wind is wind coming from the north to the south. And because water has a higher heat capacity than land, it absorbs a lot of energy, and it's responsible for a lot of our overall wind patterns and climatic patterns, particularly because water absorbs so much energy, has a high heat capacity. It's responsible for moving heat around the globe, keeping certain areas ice-free and resulting in other areas being more iced over. So here is some examples of prevailing wind patterns. Now this is, there's a few things happening here. One is you have a number of H's and L's. These are high and low. So high and low atmospheric pressure. And then the arrows represent the direction of the wind. So let's look at this one off the west coast of the US. So we have a high pressure system out here and a low pressure system off California, Baja. High pressure, low pressure. Wind or atmospheric air moves the same way water would. If you have a high spot and a low spot, and you pour a bunch of water on the high spot, it's going to move towards the low spot. So the wind or the air is going to want to move, the air is going to want to move from the high spot to the low spot. So it's going to go from here to here. But our arrow is pushing south. Position yourself at the H. Pretend you're looking at Baja or Southern California, and you're trying to move there, right, in a straight line. What's happening is then here Coriolis is grabbing you and pushing you to the right. So we have a high and a low. We want to move from the high to the low, but Coriolis is moving us to the right, which in this case is south. In the southern hemisphere, it would be the opposite of that. So these lines indicate pressure differential. So same thing here, a high and a low. Wind wants to move there, and it's moving to the right and go in that direction. So this is actually bringing warm air from the Atlantic to northern Europe here. Prevailing wind patterns. So here we've got a high pressure and a low pressure. This is gyre. So the high pressure to the low pressure, wind or atmosphere wants to move this way, air wants to move this way. It's caught by Coriolis. It's moving to the left towards the equator here. And similar thing here. High pressure, low pressure, atmospheric air wants to move towards the low pressure. It's getting pushed to the left, surrounded by low pressure systems, so it creates these gyres here. In the ocean, upwelling and downwelling are the two really drivers of what happens and where. And upwelling is just the bringing of cold, typically saline, typically nutrient-rich water to the surface. And downwelling is the opposite of that, where denser water then moves deeper and then is recirculated back around. And so it's a conveyor belt system. In our area, upwelling is really important. And so you've got winds that move across the coast, and then water is moved to the right, is pushed off the west coast. And so here, kind of just was angled slightly differently, but if you can think of this as like BC, Washington, Oregon, wind is moving from the south, and then surfaces are pulling the water out. Water's moving to the right. And as you look at the graph, water's actually moving to the left, but imagine yourself as the wind. And so face yourself at the U.S.-Canadian border and look towards the states, look towards Washington. With wind to your back, it's a southern wind. It's a northern wind. It's coming from the north, moving to the south. So the northern winds coming from the north, going south, that water's moving, or sorry, that wind is moving past you, moving down the coast of Washington, and then the water's moving to the right. It's called Ekman transport, but it's the same as, it's driven by Coriolis as well. And so in the northern hemisphere, the result is 90 degrees. So if the wind is coming through your nose, the water movement's going to be to the right. This is a bit funny because it's like at an angle and a kind of counterintuitive. But what we can see here is as we have southern wind. Sorry, keep mixing those up. Northern wind moving in a southerly direction. Water's moving offshore, and then below here we can see a number of temperatures, and so these are thermoclines. Cline meaning difference, thermo meaning temperature. Warmer water's at the surface because it's less dense, colder water's down below. So as water is pushed offshore, this cold water comes to the surface, and that cold water is typically saltier, typically has a lot of nutrients, and those nutrients are what's required for phytoplankton to bloom. This diagram is pretty interesting. So this is sea surface temperature, and you might expect that it would be colder off the coast of Washington than it would be off the coast of Northern California. But due to the massive amount of upwelling there, it's actually colder off Northern California than it can be off our coast. In fact, as divers and surfers know, the water is actually warmer in lots of areas in the winter because of less upwelling than it is during the summer. Because summer there's so much upwelling, so much cold water being brought to the surface, which is one of the reasons those areas are very ecologically productive. So upwelling brings nutrients to the photic zone, to the lit zone, which is fertilizer, effectively, nutrients that phytoplankton need to grow. And so phytoplankton need light and nutrients, and by bringing the nutrients to the light, phytoplankton can grow and be happy, and zooplankton or other consumers eat those, and then fish, whatever, eat from there on out. So really these nutrients provide phytoplankton blooms, which then feeds the secondary productivity. And then this is all part of this global ocean conveyor belt, which is really interesting. So this is why areas of the northern United States can be quite warm with this Gulf Stream coming up, crossing over, downwelling here, moving further around, and ultimately that water moves in the deep current, so thousands of feet below the surface, comes back up in the North Pacific, is upwelled, and then moves back around. And this great conveyor belt is what keeps a lot of our areas ice-free. It's why if you look across the same latitude, you can have a variety of different climatic conditions based on your relationship to these ocean currents. It's thought that a large pulse of fresh water shut this down, or could shut this down, and cause dramatic climatic impacts as well. So globally, you see, I'm going to go a little bit more here, and then we're going to pause and jump to the next lecture. I'm trying to keep them a bit short. So precipitation's obviously very important, and annual temperature become progressively cooler from the equator towards the poles. Okay, there's deviations due to ocean currents that can help keep areas warm. And the air temperature over land can vary more than more coastal areas. Again, using the eastern and western Washington example, because of our proximity to the water, our climate's more tempered than it would be at the same latitude in eastern Washington. And you can see some of this play out in these ocean conditions here, as well as, so like this, like warming up here is driven by that conveyor belt. So you can be warmer here than you are, say, at the same latitude over here. So this conveyor belt, and then moving that warm water across the Pacific here as well. This is annual seasonal temperature variation. So this is the difference between the max and the min, and you can see in lower latitudes, equatorial system is quite low. But if we look across this area, you can see massive temperature variations because there's very little oceanographic influence. Same here and here. So as we move closer, we can just draw a line from here over. If you just follow this latitude, was at 65 across, you can have 10 degrees temperature variation all the way up to 60 degrees Celsius temperature variation, which is massive. All driven by variations of how close they are to oceanographic currents and what those oceanographic currents are doing. You can even see it in Australia here, where the maritime systems are pretty stable, and then as you go further to the interior, you have more variation. And temperature also decreases with elevation above sea level, lapse rate. So it's colder right now on top of Mount Baker than it is down here in lowland Bellingham area. Air pressure and density decrease with elevation. There are fewer air molecules to absorb infrared radiation, and wind speed increases due to less friction as well. Precipitation patterns associated with the atmospheric circulation cells are modified by mountain ranges and semi-permanent high and low pressure zones. So we'll take a look at this. Let me jump to here. So mountains influence regional climate, specifically the rain shadow effect. And so again, eastern Washington, like parts of eastern Washington, are desert ecosystems. Even though they get quite cold, they don't have a lot of rain. Some areas are about 7 inches or less annually, where Seattle's 14, I want to say 14. We're a little bit more than that. This is due to the rain shadow effect. And so as we have evaporation over the ocean, that vapor-laden water moves up to the mountains, is pushed up higher, loses energy, water precipitates, falls down, and then that air then moves over the mountain, and it's lost most of its water vapor at that point in time, so it's a lot drier. So that's why we have the rainy and the dry side of islands, or of mountains and islands as well. Sorry. So you want Hawaii. Even the San Juans, you'll see that as well, on western facing slopes versus eastern facing slopes, entirely different vegetative communities on a very small scale, but you'll still see that same thing. It's really quite striking. So we'll stop there and we'll come back to a couple other climate impacts, and then I want to spend a bit of time talking about the PDO, Pacific Decadal Oscillation. So, oops, jumped around. So we'll check back in for part 2 shortly here.